Okay, this week we're going to go over sequences. Now, before we get into what a sequence is, I'd like to just briefly review two of the functions that we've studied this year, linear and exponential functions. Now, linear functions model situations where the rate of change is constant, or where we are repeatedly adding the same value to some initial value. They can be modeled using the equation y equals mx plus b. And we can see that this equation describes what a linear function models. So here we have our initial value, the y-intercept, and we're adding the value m, or the slope, x number of times. So we're taking b and we're adding m plus m plus m plus m x number of times. And that gets us an output y. Exponential functions model situations where the ratio of change is constant, or where we are repeatedly multiplying an initial value by some constant factor. They can be modeled using the equation y equals a times b to the x, where a is our initial value, and we're repeatedly multiplying a by a factor of b x number of times. So let's take a look at arithmetic sequences. So what is an arithmetic sequence? Well, it's a sequence of numbers such that the difference of any two successive members of the sequence is constant. Well, what does that mean? So let's take a look at this example. 1, 4, 7, and 10. What do you notice about that sequence of numbers? Well, you might have said that there's a difference of 3 between them. 1 plus 3 is 4. 4 plus 3 is 7, 7 plus 3 is 10, and so on and so on and so on. So if we read this definition again, a sequence of numbers such that the difference of any two successive members, or elements that are right next to each other, 1 and 4, members of the sequence is constant. The difference between those two members is constant. The difference between 1 and 4 is 3. The difference between 4 and 7 is 3. Between 7 and 10 is 3. This would be an arithmetic sequence because the difference between the values remains constant. This difference is called the common difference. Now, this sequence can be modeled using the following table and equation. Our inputs are going to be called n, which represents the term number, or where that term appears in the sequence, and a sub n is going to be our output, or the nth term. And I'll explain what that means. So the first term in our sequence is going to be 1. So n represents the order in which the terms appear. So 1 represents the first term, and the output represents the the first term in the sequence. This would represent the second term, and 4 would be the second term in the sequence. The third term is 7 would be the third term in the sequence, and 4 is the fourth term, and then 10 would be the fourth term in the sequence. And this equation right here models this data. So let's test it. Let's plug in a 1, see if we get a 1. So a sub n equals 1 plus 3 times 1 minus 1. Well, 1 minus 1 is 0, times 3 is 0, plus 1 is, and so the first term would be 1. Let's try the third term. So a sub 3, or the third term, would be equal to 1 plus 3 times 3 minus 1. 3 minus 1 is 2, 2 times 3 is 6, and 6 plus 1 is 7, and so the third term would be 7. All right, you're about to watch a video where we derive this equation. So if you don't quite understand what these symbols mean, or why this n is being subtracted by 1, you're going to understand that in a second. All you need to know is this equation, or what's called an explicit equation, models arithmetic sequences. So you may be saying to yourself, well, no, wait a second. This looks a lot like linear functions. Are these linear functions? Because I totally can write a linear function to model this data. Mr. Odens, this is linear functions, isn't it? And my response to you would be, yep, these are linear functions. An arithmetic sequence is a discrete linear function where the domain is restricted to natural numbers. All right, so what does that mean? Well, discrete means there are a finite number of inputs over the course of an interval. Don't worry about that right now, but it basically means there are just certain numbers that you can plug in and other numbers that you can't. So, like for example, there can be a first term of the sequence, there can be a second term of the sequence. There can't be a zeroth term. So it would be improper to plug in a 0 in for n to find the zeroth term of the sequence because there is no zeroth term of the sequence. You can't have that. The first term is the first term. Um, and I say the domain is restricted to natural numbers because you have to start at 1 and then go to 2 and 3 and 4. Also, you can't have decimal inputs. So just like there's no zeroth term, there's also no 1.5 term or 2.79236. Those aren't in the domain of this function. All you can plug in are your natural or your counting numbers. All right, now we're going to watch a video I made a couple of years ago that goes a little bit more in depth, explaining exactly what arithmetic sequences are and how to derive this little formula and all the little parts to it. All right, so here we go. Okay, before we begin a discussion on geometric sequences, I thought I'd go through a quick review of arithmetic sequences. So if you recall, this is an arithmetic sequence. We start at 5, 7, 9, 11, 13. 5 would be our first term, so we can think of this as each term has a number or a placement in the sequence. 5 is the first term, 7 is the second, 9 is the third, and so on, fourth and fifth. And there are potentially an unlimited or infinite number of terms in this sequence. And you may notice a little pattern here. To go from 5 to 7, we're adding 2. To go from 7 to 9, we're doing the difference, or we're doing the same. To go from 9 to 11, again adding 2. And from 11 to 13, we're adding 2. And this repeated addition of 2 is what we call the common difference. So this is called the common difference. And this is all well and good, but let's say we wanted to predict the 100th term of this sequence. We could add 2 100 times, but it's easier to create a formula that will get us there because then we can generalize that formula to all sequences and not just this sequence. So let's see if we can derive that formula somehow. So let's make a function table. Actually, let's not use x. Let's use n for the term number and a sub n for the actual term. So let me define these variables for you. N refers to the placement in the sequence. So 5 is the first term. So if we were to write if n equals 1, then the first term is going to be 5. So when n is 1, a sub n is 5. And so the second term is 7. The third term is 9. The fourth term is 11, and the fifth term is 13. And in fact, I'm not going to need all of these to show you what to derive the formula. And I'm going to need some space. So let's just use the first 3. So one way of looking at this is 5 is equal to itself. We know that 5 is equal to 5. We can also say that 7 is equal to 5 plus 2, and 9 is equal to 5 plus 2 plus 2. Now, why would I describe the successive terms in the sequence using multiple additions of 2? Well, 2 is the common difference, and the way you generate more terms in the sequence is you just keep on adding the common difference a certain amount of times. And if you notice, to get the second term, we added the common difference 1 time. To get the third term, we added the common difference 2 times. So I'm actually going to write this a slightly different way. Since we're adding the common difference 1 time, I'm going to say that this is 5 plus 2 times 1. And if we're adding the common difference 2 times, I'm going to write this as 5 plus 2 times 2. And just to remain consistent, I'm going to write this as 5 plus 2. And since we're not adding the common difference at all, this will be 0. So now I want to ask myself the question if I want to predict any term. So let's say instead of the term number being 1, 2, 3, let's say the term is just n, an unknown term. Then a of n, the term, would be what? Well, we know we're starting with 5, and we're adding the common difference a certain amount of times. And how many times are we adding the common difference? So let's analyze the relationship between the number of times we're adding the common difference and the value of n, the term number. So if in the first term we're adding the common difference 0 times, the second term we're adding the common difference 1 time, the third term we're adding the common difference 2 times, so it seems like we're always adding the common difference 1 less times than the term number. So how would we write 1 less than the term number? Well, we write the term number and then we subtract 1 from it. And generalizing this form, or we can say that the nth term of this sequence is going to be 5 plus 2 times the difference of n minus 1, or n and 1. If we want to generalize this formula to all sequences, we can say that this is just the first term in the sequence, the first term, and this number is going to be the common difference. The common difference. And so this can be generalized to all sequences by writing a sub n, or the nth term, is a sub 1, or a1, the first term in the sequence, plus the common difference times n minus 1. And that is the formula for an arithmetic sequence. All right, let's review what we just saw in that portion of the video. So for this first task, I want you to explain what each variable in the following explicit formula for the nth term of the sequence represents. So we've got four variables here, a sub n, a sub 1, we got our d, and our n. So pause the video and just jot down what you think each symbol or each variable represents. Pause the video now. Let's see how you did. So a sub n represents the nth term. A sub 1 represents the first term of the sequence. D represents the common difference. And n represents the term number. All right, so we'll see an example over here in this next task. So what is the first term of the sequence defined by the explicit formula below? What is the common difference? And list the first 5 terms of the sequence. All right, so pause the video and see if you can do those 3 tasks now. Let's see how you did. So what is the first term of the sequence? Well, we know that the first term of the sequence is defined by this variable right here, a sub 1. All right, and looking at the form of this explicit formula, I see that 4 right here, all right, is our a sub 1. So 4 is the initial value or the first term of the sequence. What is the common difference? Well, the common difference would be what n minus 1 is being multiplied by, so that would be 6. And if I wanted to list the first 5 terms of the sequence, I could start at 4 and then repeatedly add 6, or I could plug in 1, a 2, a 3, a 4, and a 5, and whatever a sub n would be our first 5 terms. And so there we go. The first term is 4, the common difference is 6, and the first 5 terms are 4, 10, 16, 22, and 28. And finally, simplify the explicit formula below. What do you notice? Is there another way you could rewrite this equation? So why don't you pause the video, simplify, which means if there's anything that you can do, any multiplication to perform maybe, any terms to combine, do all that until you can do nothing else, and then you've simplified the expression on the right-hand side. So pause the video and let's see how you do. All right, so you should have gotten a sub n equals 3n minus 1. So a sub n is our nth term, where n is our input, or the term number. Right? This looks very much like our linear equations that we've studied for going on 2 years now, in 7th and in 8th grade. And this can be rewritten as a linear function, where a is our output and n is our input. And so if you had trouble kind of deciphering what this symbol means, we went over subscripts earlier in the year. This is just a description of this variable. A is our output, and n represents the term number of that output. That's why we call it the nth term. So if we wanted to find like the second term, this would be a sub 2, and n would be equal to 2. This notation is reserved for arithmetic, and we'll learn about geometric sequences in just a second, but sequences in general. But here's the same exact idea represented in function notation. Now, I make this, or I draw this parallel because I want you to understand that all we're doing is we're looking at a special type of linear function in a special type of way. And you might think, why are we doing this? I'd rather just write a slope-intercept form. And believe me, I'm right there with you. I'd like to write slope-intercept form too. But as you move forward in math, you're going to be working with sequences later on in higher level math classes. And just as sometimes we need to describe linear functions using standard form because it's a little bit more appropriate for the problem we're trying to solve, and slope-intercept form doesn't really work very well with our model, arithmetic sequences, or just describing sequences in general, is very important when we're working with sequences. It makes more sense to describe it this way than it does this old way using slope-intercept form. So that's the purpose of studying sequences in the first place. That's why you're learning yet another way to rewrite the same idea. So let's get some practice with sequences. What I'd like you to do is write an explicit formula for each of these sequences, and then use the formula to find the 91st term. So I'm not going to tell you what to do here. Let's see if you can figure it out on your own. All right, your goal is to write an arithmetic sequence, which means, all right, we need a first term of the sequence and a common difference. And once you have that, you can easily find the 91st term. So get cracking. Let's see how you do. Pause the video now. All right, let's see how you did. All right, so here for our first sequence, we have an initial value, or our first term is 7.5, and the common difference is 2.5. So that allows us to write our explicit formula. And here it is right here. Our initial value, or our first term, is 7.5, and our common difference is 2.5. So if we wanted to find the 91st sequence, the 91st term, all right, the value of n would be 91, because n is the term number. So we plug in that n, all right, simplify, and now we can describe a sub n, or the 91st term, is equal to 232.5. All right, let's see the next two. So our common difference was 0.004. Our first term was 0.001. We can derive our formula and use it to find the 91st term, which would be 0.361. All right, now on this one, if you noticed, all right, the common difference was -3. And the first term was 4. So this is an example where where the difference is negative, or we're subtracting from our first or initial value. All right, so the explicit formula would be 4 minus 3 times n minus 1. And now we can find our 91st term the same exact way. And so what we get is the 91st term, or a sub 91, is equal to -266. All right, let's review some simple algebraic concepts. If we want to find the value of one variable in a formula, how many other values do we need to know? We need to know all the other values. All right, we can only solve equations that have one unknown right now, not 2 or 3. All right, so if we wanted to know excuse me. What do you need to know in order to determine the term number, so the value of n? What do you need to know if you want to find n? Well, if we want to find n, we need to know everything else. We need to know the nth term, we need to know the first term, and the common difference. What do we need to know in order to determine the nth term? All right, a sub n, we need to know the first term, the common difference, and the term number. What do you need to know in order to determine the common difference? All right, well, what would be helpful? One way to do this is to know the nth term, the term number, and the first term in the sequence. And then finally, what do you need to know in order to determine the first term? Now pay very close attention to this question. If we want to know the first term in a sequence, well, we'd have to have an nth term and know where that term appears in the sequence, and we need to know the common difference. So, armed with this knowledge, I would like you to attempt the following 3 problems. I'm not going to tell you what to do. Explore it on your own. See how well you can get the answers without my guidance. Pause the video now. Okay, so the first question says the 9th and 10th terms of an arithmetic sequence are 62 and 65.5 respectively. What is the first term? Well, let's see. Do we know the first term? No. Do we know the common difference? Well, because these terms are right next to each other, the 9th and 10th term are 62 and 65.5, we can't figure out what the common difference is. And we know that the 9th term is 62, so that tells us a term number, and that tells us, the term number and the nth term. In this case, the 9th term would be 62, so that gives us 3 out of the 4 unknowns, so we can solve the equation for a sub 1, or the first term. So the common difference is 3.5. We know that the 9th term is 62. Solving for a sub 1, that gives us 34. So 34 is the first term in the sequence. Now, alternatively, you could have used the 10th term is 65.5 with the same common difference, and you could have found that the first term is still 34. If you have all this information, I suggest figuring out the first term from both pieces of information just to verify that you've done everything correctly. All right, so for the second one, the 20th and 26th terms of an arithmetic sequence are 100 and 124 respectively. What is the first term? All right, so let's find the common difference. Now these values or these terms in the sequence are not right next to each other. They're 6 terms apart. So if we take the difference between 100 and 124, that's a difference of 24 units over 6 terms. So that gives us a common difference of 4. Another way you could have figured it out is you start at 100, which is the 20th term in the sequence, and 6 terms later you're at 24. So you add the common difference 6 times and you get 124, and solve for D, and you get the common difference is 4. And so now, using the information in the problem, you can solve for the first term. The 20th term is 100. Solving for a sub 1, you get 24. And alternatively, you could have used the 26th term in the sequence, which is 124. And the solving for A1, you get 24. All right, so the last problem, the 28th and 32nd terms of an arithmetic sequence are 115 and 127 respectively. What is the 2015th term of the sequence? So we take a similar approach. We find the common difference, either using the model I suggested or just using these as your inputs, those as your outputs, and calculating a rate of change. But the common difference is 3. All right, then using our explicit formula, the 20th term is 115. Solving for the first term, we get 34. And using our explicit formula, we can find the 2015th term. So we plug in 2015 for n, and we get out the 2015th term, which is 6,076. So our next kind of sequence is called a geometric sequence. And a geometric sequence is a sequence of numbers such that the ratio of any two successive members of the sequence is constant. So what does that mean? Well, that means if we start with a 1 and we go to a 3 and then a 9 and then a 27, this would be a geometric sequence because the ratio between the values remains constant. All right, and what do we mean by the ratio? That means 3 over 1 would be 3, 9 over 3 would be 3, 27 over 9 would be 3, and so on and so on and so on. It seems like we're starting with a first term in the sequence and we're constantly multiplying by the same value or the same factor. Now the ratio between these members in the set is called the common ratio. And the sequence can be modeled using the following table and equation. Here's our table, there's our equation, and all of the variables mean the same thing. N represents the term number, and A sub n represents the nth term. So the first term in the sequence would be 1, the second term would be 3, the third term would be 9, and the fourth term would be 27. And the explicit formula is A sub n equals 1 times 3 raised to the n minus 1 power. Now you're probably saying to yourself, well, wait a second, Mr. Odens. This too looks familiar. It looks kind of like exponential functions. Are they the same thing? Well, surprise, surprise. They are the same thing. A geometric sequence is just a discrete exponential function where the domain is restricted to natural numbers. And the whole explanation about why this is the case that I went through for arithmetic sequences applies to geometric sequences as well. So now you're going to watch another video I made in the past that goes into geometric sequences a little bit more in depth, and I go through a bunch of examples. And once you're done with that, you can watch the, after you're done watching the video, please complete the two skills tasks that I've given you this week. There are no performance tasks. You're welcome. Okay, so now let's take a look at geometric sequences. This is an example of a geometric sequence. We start with 1, we go to 2, then 4, then 8, then 16. And in the same way that an arithmetic sequence is just a sequence of numbers, and each number has a placement in the sequence, so does a geometric sequence. So 1 is the first term, 2 is the second term of this sequence, 4 is the third, 8 is the fourth, and 16 is the fifth. Now, unlike an arithmetic sequence, we're not adding a common difference. So to go from 1 to 2, we're adding 1, and then to go from 2 to 4, we're adding 2. So you can already see this is not a common difference. From 4 to 8, we're adding 4, and from 8 to 16, we're adding 8. So that's not really going to work for us. As mathematicians, we like to find or describe patterns in the simplest way possible. So what you might find is to go from 1 to 2, we multiply by 2. We're not adding, but we're multiplying. To go from 2 to 4, again, we multiply by 2. From 4 to 8, multiplication by 2. And then from 8 to 16, multiplication by 2. So we're just multiplying by 2. And in arithmetic sequences, we call this the common difference, but since we're multiplying, we call this the common ratio. And I'll show you right now why it's called a common ratio. So let's take the number 16 and let's compare it to 8. Let's create a ratio. What is 16 to 8? Well, 16 over 8 is the same as 2 over 1, which is just 2. If we compare 8 to 4, create a ratio there. 8 over 4 is just 2 over 1, which is 2, and so on and so on. 4 to 2 is just 2, and then 2 to 1 is just 2. So as you can see, any way you compare successive terms in the sequence, you're going to get the same ratio. So there's a common ratio. Now let's see how we can use this common ratio to derive a formula for a geometric sequence in the same way we derived a formula for an arithmetic sequence. So we'll start with the same function table where n is our nth term, the term number, and a sub n is the nth term. So our first term is 1, our second term is 2, our third term is 4, and let's go to a fourth term here. Our fourth term is 8. All right, 1 is just 1. Notice I'm starting out the same way. 2 is just 1 times 2. 4 is just 1 times 2 times 2. And then 8 is just 1 times 2 times 2 times 2. So if we isolate this part of the expression, we can see a pattern here. We're just multiplying 2 by itself a certain number of times. And just as repeated addition is what we call multiplication, repeated multiplication is what we call exponentiation. So there might be an easier way to write this, and we're going to write it like that right now. So I'm going to say that this is going to be 1 times 2 to the 1, since we're just multiplying by 2. 4 is equal to 1 times 2 squared. 8 is equal to 1 times 2 cubed. And to remain consistent, I'm going to say that 1 is 1 times 2 to the 0. Now, y to the 0, if you recall, anything to the 0th power is 1. So x to the 0 is just going to be 1. Anything to the 0th power is 1. So this evaluates to 1 times 1, which is equal to 1. So how could we generalize this to the nth term? Here's n. So a sub n, the nth term, is going to be 1, our initial value, our starting value, times 2, the common ratio, to what? Well, let's look at the relationship between n, the term number, and our exponent. So if the term number is 1, to generate the first term, we raise 2 to the 0th power. To generate the second term, we raise 2 to the first power. To generate the third term, we raise 2 to the second power, and so on and so on. The same relationship that we observed in an arithmetic sequence holds for a geometric sequence. We're always raising the common ratio to 1 less than the term number. So that's going to be, let me write that a little clearer, n minus 1. And 1 here is our first term, and 2 is our common ratio. So we can generalize this formula for all geometric sequences by saying the nth term, a sub n, equals the first term, a1, times the common ratio r. We're going to use r instead of d because it's not a common difference, it's a common ratio. And we're going to raise it to the power of n minus 1. And that is the general form of, or that's the formula for a geometric sequence. Okay, let's use what we know about geometric sequences to write some explicit formulas. So in this problem, we're asked to write the explicit formula for this geometric sequence and then determine the 12th term. So let's start with our formula, a sub n equals a1 times r to the n minus 1. And in order to write the explicit sequence, we're going to have to determine the first number in the first term in the sequence and the common ratio. So the first term in the sequence is going to be very easy. It's just this right here, 5. So that was easy. And then we're going to have to determine the common ratio. So what do we do to go from 5 to 15 that we also do to go from 15 to 45? Looks like 5 times 3 is 15, and 15 times 3 is 45. So that was simple. Our first term, A1, is going to be 5, and our common ratio, R, is going to be 3. So we're now ready to write our explicit formula. Our explicit formula is A sub n, the nth term, equals our first term, 5, times our common ratio, 3, raised to the n minus 1 power. Now they tell us to determine, or our next step is to determine the 12th term. So we know that the 12th term, a sub 12, equals 5 times 3 to the, and since n is 12, we're going to put 12 right here, and we're going to take away 1 from 12. And so all we have to do is evaluate the expression 5 times 3 to the 11th power. And as you'll see, this formula comes in handy because we're going to end up with a very, very large number. 3 to the 11th power is 177,147. And then when we multiply that by 5, we get 885,735. So the answer to our question is our explicit formula is a sub n times 5, or equals 5 times 3 to the n minus 1, and our 12th term is 885,735. Okay, let's try another problem. Write the explicit formula for the geometric sequence, then determine the 6th term. So we're going to start out with our formula, a sub n equals the first term, a1, times the common ratio raised to the n minus 1 power. So we need to identify our first term. That one's easy. Our first term, a1, is going to be 100. But the common ratio is going to be a little different. You might be tempted to say that to go from 100 to 50, you're dividing by 2. But that's not really a ratio when we say division by 2. Or if we're going to say it's division by 2, we're going to have to write that a different way. So to write this as a ratio, we're going to create a ratio. What is 50 over 100? Should be the same as comparing 25 to 50. 25 to 50, since the ratio should be common. And sure enough, 50 over 100 and 25 over 50 both reduce to 1/2. And 1/2 is our common ratio. And for those of you who are familiar with the idea that every division problem is just a multiplication problem in disguise, will understand that I'm going to rewrite this division by 2 as multiplication by our common ratio, 1/2. So 50 times 1/2 is 25, and now we've identified, our common ratio. R is going to be 1/2. And so now we can write our explicit formula, a sub n equals our first term, 100, times, I'll put this in parentheses, 1/2 raised to the n minus 1 power. Now, to find the 6th term, or a sub 6, equals 100 times 1/2 to the 6 minus 1 power, or in this case, the 5th power. And for those of you who remember your rules of exponents, in this case, we can distribute this to the numerator and the denominator, the exponent to the numerator and the denominator. So that's going to be 1 to the 5th power over 2 to the 5th power. And that just simplifies to 100 times 1 over 32. And so I'll continue this over here. And that's just going to be 100 over 32. And if we use our calculator, that probably comes out to a nice decimal, 100 divided by 32 is 3.125. And so there we go. The answer to our question is, this is the explicit formula for the sequence. A sub n equals 100 times 1/2 raised to the n minus 1. And then our sixth term is 3.125. Okay, so why don't you pause the video and attempt this problem on your own before I explain it. So let's pause the video now. Okay, so let's start with our explicit formula, or the general formula for an arithmetic sequence. This procedure should be fairly familiar to you by now. All right, so our first goal is to find the first term of the sequence, and that's always easy when you're given the first few terms of the sequence. So our first term is -6. Our second goal is to find our common ratio. So what do we do to -6 to get 18? Well, it's the same thing we do from 18 to -54. So I'm going to show you a different way of looking at this. That is essentially another way of finding the common ratio. So before I was telling you, take the first term and the second term and compare them, putting the second term over the first term and then putting the third term over the second term. So we'd put 18 over -6. That would give us our common ratio, -3. And if we do -54 over +18, that also gives us -3. And that's fine, that works. But now I'm going to show you why that works. We're going to model this using an equation that helps us answer the question, what are we doing to -6 to get +18? What are we multiplying -6 by? So we can write that as an equation. -6 times this common ratio r gives us a +18. And as you see, when you solve for r, what you get is the ratio that we have been writing down. And if you ask the same question, what do you do to 18 to get -54? Well, if you start out with 18 and you multiply it by the common ratio r, and you get a -54, well, when you solve for r, you're going to get that same ratio, -54 over 18. And both of these simplify to -3. So our common ratio is -3. So this may seem a bit simplistic for this sequence, but when we get to the next question, you will see why analyzing or answering this question in an algebraic fashion becomes very, very useful. Sorry, times -3, and here we're multiplying by -3, so our common ratio is -3. So now we can write the explicit formula for the sequence. A sub n equals our first term, -6, times -3 raised to the n minus 1 power. So now let's find the 10th term. A10 equals -6 times -3 raised to, and in this case, this is going to be 10 minus 1. That's going to be -3 to the 9th power. And we know that a negative number raised to an odd power is going to be a negative number. So we'd expect a negative number. And, sorry, -3 to the 9th. That's a little better. Okay, -6 times -19,683. And now when we multiply that by -6, we get a positive number, 118,098. So we've answered our question. Here's the explicit formula for the sequence. And here is our 10th term. Okay, so pause the video and attempt this one on your own. So let's start out with our model times r to the n minus 1. And same old, let's find the first term in the sequence. A1 is 3.15. Now, again, that's the easy part. Finding the common ratio is going to be, or takes a little bit of analysis. So you know how to find the common ratio comparing these two terms, but I'd like you to get used to creating a model. So we're going to ask ourselves, what are we doing to go from 3.15 to 6.615? What are we multiplying by? 3.15 times the common ratio r equals 6.615. And that's how we get this fraction, 6.615 over 3.15. Now, at times we're just going to have to keep it as a fraction like this, but if you plug that into your calculator, let's see what we get. And we get a nice decimal 2.1. Very nice. So our common ratio is just going to be 2.1. So I feel comfortable using that in our explicit formula. That's easy to work with. So our explicit formula is going to be a sub n equals our first term 3.15 times 2.1 raised to the n minus 1 power. Now if we're looking for the 15th term, then A15 is going to equal 3.15 times 2.1 raised to the 15 minus 1, which is going to be the 14th power. And then if you just put this into your calculator exactly as it looks, you will get 102,183.4779. So our answers are here, the explicit formula and the 15th term. And I should take a few moments to point out that the reason that you should understand how to model this problem algebraically and solve for it is because the common ratio here, multiplication by 2.1, was not obvious. And when you're working in a math class, you get problems that look more like 2, 4, 8, 16. But when you're working in the real world, your measurements of real world data are not always so clean. They look more like this. And so to find the common ratio is going to take a little bit more effort on your part. All you have to do is create a model of the question that you are asking and then solve for the unknown. In this case, the common ratio r.